Kepler 16b forced astronomers to admit that Tatooines are real, not a sci-fi mirage, not a cinematic trick, but a kind of planet that may be erased by Einstein long before most of them become easy to find. That is the reversal. Circumbinary planets are worlds that orbit two stars instead of one. And the deeper possibility is unsettling. The same gravity that builds elegant orbits may quietly make many of those systems unstable, starved, or dead on arrival. In 2011, NASA's Kepler mission confirmed Kepler 16b, the first unambiguous planet orbiting two stars. It circles a pair of suns every 229 days, about 245 light-years from Earth. For a moment, it felt like science fiction had been redeemed by reality. But the celebration came with a strange silence. We did find some circumbinary planets: Kepler 16b, Kepler 34b, Kepler 35b, later TOI 1338b. Yet, compared with how common binary stars are, the universe seems oddly stingy with stable, comfortable Tatooine-style worlds. Nearly half of Sun-like stars are in binary or multiple systems, according to studies like Raghavan et al. 2010. If two-star systems are that common, why don't Tatooines flood our catalogs? One answer is observational bias. Planets around two stars are harder to detect because the stars move, eclipse, and scramble the timing that astronomers rely on. That part is true. But it is not enough. Not enough! There is a harsher possibility. The problem may begin before the planet is even fully assembled. In a binary system, the stars do not sit still. They whip around a shared center of mass, dragging space-time with them in a changing gravitational dance. A young planet forming in the surrounding disk is not orbiting a calm lighthouse. It is circling two swinging hammers. And once Einstein enters the room, the story gets sharper. General relativity slightly shifts the orbit of the binary itself. The closest point in the star's orbit can precess, meaning it rotates over time. On paper, that sounds tiny. In a delicate system, tiny is enough. It is like balancing a coin on a washing machine while someone keeps changing the spin cycle. Researchers studying circumbinary dynamics have shown that planet formation already happens near a dangerous boundary. In 1999, Holman and Wiegert estimated a critical stability limit for planets around binaries. Get too close, and long-term orbits fail. Many of the circumbinary planets Kepler found sit just outside that limit, almost as if they piled up at the cliff's edge. That alone is fascinating. It suggests these planets do not enjoy wide safety margins. They survive in a narrow orbital strip, a cosmic shoulder lane pressed against chaos. Personally, I think that detail changes the whole emotional tone of the search. We are not looking for abundant desert twins under double sunsets. We may be catching survivors that formed in the least forgiving architecture imaginable. Then came another clue. In 2022 and 2023, observations with ALMA and other instruments kept showing that disks around binary stars can be warped, truncated, and stirred. Some are misaligned. Some are broken into rings. Some seem to lose the quiet circular conditions that help pebbles settle into planet-building seeds. Imagine trying to build a snowman on a merry-go-round while the floor tilts every few seconds. That is much closer to the problem than the word disk makes it sound. So what is Einstein doing exactly? Not blasting planets apart like a movie explosion. something colder. Relativity can alter precession rates and resonances inside the binary system. Those small changes can move where gravitational nudges accumulate. Over hundreds of thousands or millions of years, that can stir up planetesimals, raise collision speeds, and turn gentle sticking into violent shattering. Rock stops acting like wet clay and starts acting like bullets. This matters because planet formation depends on slowness. Dust has to clump. Pebbles have to settle. Kilometer-sized bodies have to merge without smashing themselves back into gravel. Around a single calm star, that process is already difficult. Around two stars, it can become a demolition site. Around two stars whose orbits are subtly sculpted by relativistic precession, some regions may be even less forgiving than older models assumed. So let me ask you this. Do you think the real bottleneck is detection bias? Or are most Tatooine systems genuinely born hostile? Tell me which side you lean toward. There is a reason astronomers care about this beyond movie nostalgia. Circumbinary planets test whether planet formation is robust or fragile. If planets can grow almost anywhere, then the universe is generous. If two stars are enough to ruin the recipe most of the time, then habitable real estate may be rarer than we like to imagine. And there is a deeper irony here. Einstein is usually the name we invoke when talking about black holes, gravitational waves, extreme things. But relativity does not only matter in spectacular catastrophes. Sometimes it appears as a quiet accountant, shaving stability from an orbit one fraction at a time. Like a thermos in a blizzard, a young planet does not need the whole environment to become impossible. It only needs the heat loss to beat the heat gain for long enough. The evidence for this broader fragility is indirect, but serious. Kepler found roughly a dozen confirmed circumbinary planets, not hundreds. Most are large, likely because bigger planets are easier to detect. Many orbit close to the inner stability limit. That pattern could mean the hidden population is huge and we are simply missing it. Or it could mean the systems that survive are the lucky ones, parked in the few lanes where chaos never fully wins. David Martin and colleagues have modeled how binary star evolution and orbital dynamics can reshape circumbinary habitability over time. Other teams have shown that migration through the disk may help some planets reach the narrow safe zone after forming farther out. That sounds hopeful until you realize what it implies. The planet may need to form far away, migrate inward, stop at just the right distance, and avoid later instability. That is not impossible. It is just a very demanding audition. Confessionally, I find that more moving than discouraging. A two-sun planet stops being a fantasy postcard and starts looking like a survivor crossing a minefield. Can you imagine a sunset on a world that only exists because a few resonances happen to miss each other by a tiny margin? But wait, there is a twist that makes this even stranger. Einstein may not only reduce the number of circumbinary planets, he may also help hide the ones that do survive. If relativistic effects shift binary orbits and timing even slightly, they can complicate the transit patterns astronomers use to confirm planets. Around a single star, a planet crosses with a regular rhythm, like a metronome. Around two stars, the rhythm lurches. Add precession and changing geometry, and the signal can look less like a drumbeat and more like footsteps in a crowded station. You can still find them. You just need patience, luck, and enough observing time. So the missing Tatooines may be suffering a double sentence. Some never form cleanly. Some form and then fail. Some survive, but hide inside data that looks too messy to love. That is the real reversal in this story. The universe may not be withholding a famous fantasy for one reason, but for several stacked on top of each other. Then, think about the time scale. Protoplanetary disks often disperse in roughly 1 to 10 million years. If a binary system spends that window constantly stirring the material, the chance to build a stable planet can close quickly. 1 million years sounds enormous on human terms. In cosmic construction, it is barely enough time to pour the foundation before the ground starts shaking. This is where the title becomes personal. We are not just asking why astronomers have not found more Tatooines yet. We are asking whether many of them were quietly prevented from existing at all. Not hidden treasures, not delayed discoveries. Empty blueprints. Oh, if that reversal hit you as hard as it hit me, leave a like. Just this possibility alone turns a familiar sci-fi dream into a much harsher universe. And still, some do survive. Kepler 16b is real. So are other circumbinary worlds. Their existence matters because every one of them proves chaos does not always win. Nature left us a few examples, like train tracks threading through a collapsing hillside. Narrow, but passable. That may be the most human part of this whole story. We grew up imagining twin sunsets as common enough to belong to fiction. The cosmos may be telling us the opposite. Beauty under two suns is possible precisely because it is difficult. Personally, that is hard to shake. The iconic view may be rare not because imagination overshot reality, but because reality demands almost absurd precision before it allows that view to exist. So where does that leave us now? With better telescopes, longer baselines, and more patience. Missions like Kepler opened the door. TESS has added candidates. Future surveys and improved dynamical models may tell us whether the galaxy is full of hidden circumbinary worlds, or whether Einstein really has been trimming the population all along. Either answer is profound. If we find many more, then life-friendly architecture may be more resilient than we feared. If we do not, then one of our most beloved cosmic images was never common in the first place. It was a narrow exception, written in gravity. Kepler 16b gave us proof that Tatooines can exist. Einstein may be the reason so many others never got the chance. If rare cosmic survivors like this fascinate you, subscribe. This channel is for people who want the universe to feel bigger, stranger, and a little less comfortable every week.